Record. I think we forgot to record last time, so I'll put my notes up for last time. That's all right. I've looked at the views. It's not like these are world-busting YouTube videos, but I figure they're there if you miss a day. We'll see how it goes in the after Thanksgiving. I don't know. You think I'm trying to decide? Sorry. You think it would be better for me to sit in my office and do kind of like I did the one day I was gone? Or do you think it would be better for me to come in here on the board? Christina's going to weigh in. What do you think? You were online.
Yeah.
Which was better? Which was better?
I liked it when you were writing on the paper
tablet?
and in Fluids when you had the like additional lectures and everything. I thought those were really helpful
Okay.
to follow along.
So, someone was that Christina going to say something? Someone else? Three of them?
Watch you're more comfortable with.
One more comfortable. It's easy enough to do it in my office. The only downside maybe is that, I don't know, I forgot to record, so that could be that side. I'll try and hit record. We have to make ChEn log on just at the beginning. Tell me, Dr. Tree, hit record, and then log off. Anyway. So I'll probably do that because that's, anyway, that's easy enough to do. It's the same. Okay. So let's dive in. So I wanted to kind of review just for a few minutes. So last time we started talking about Sturm Liouville theory, which is sort of our, how do we do separation of variables for more than just Cartesian coordinates? And how do we think about what we're doing when we do separation of variables? It has actually lots of other applications. So maybe some of you, I know at least ChEn was, we have a combined computational group meeting for all people that do simulations. David Lugnell gave a nice overview of Gauss quadrature, which is a numerical integration method. And actually the fundamental basis for that method is also this material. So that's also, so if you take numerical methods class from him, I think that's next semester, and you talk about Gauss quadrature, this is also motivating there. So this is really pretty general and important math, but it's super important for solving PDEs. So the basic idea we talked about was this function vector analogy. We said you can think about functions in a new way as the sort of infinite dimensional limit of a vector. And that has some consequences, and so you can think about doing linear algebra with functions. It's one of the reasons that they spend all the time they do in linear algebra talking about all the proofs and theorems and stuff that they do, because then those translate over into functions as well, and that has important implications for things like the eigenvalue problem that we're going to talk about today. So we learned that there are function spaces, just like there are vector spaces, and the most important one is this L2 because it's square integrable, which allows us to define an inner product. And that leads to this concept of, say, orthogonal functions. That's a little mind-bending. It's easy enough to imagine in a finite dimensional space what orthogonal means. But now you've got functions that are orthogonal. It's kind of a little weird if you think about the picture, but like a lot of things when you're generalizing, what really matters is the math and the picture in your mind. The sort of word that they use comes from the thing that you can physically think of, but there isn't really a physical equivalent of orthogonal. And then we said, what's also cool is that you can write, just like you can write vectors as a sum of components over these basis vectors, you can write a generalized Fourier series, which is an infinite sum with some coefficients multiplied by some basis function. And this is the thing that's really powerful about this, is now we can think about writing functions in terms of infinite sums over other functions. And there's sort of two pieces we need out of this guy if we want to be able to do this. The first is the coefficients, and the second are the basis functions. So the coefficients are pretty easy. If you can do inner products and you have orthogonal basis functions, it ends up that you can just do this. Okay, this needs orthogonality. Need orthogonal BIX. Okay, but if you have orthogonal basis functions, then you can write down the coefficients pretty easily. All you have to do is a pair of integrals. Okay, and that's not too bad usually. So the question then is, how do we go about getting these basis functions? Okay, and I think Zach asked this question. He's like, oh, well, maybe these are like any function. And so, well, hold a little bit. Okay, we got to be a little careful about how we define these because it's an infinite series of these functions. And so what we're going to find is that these kind of oscillatory functions, a lot like sines and cosines, But there are different versions of them. There's also a set of polynomial, or a bunch of sets of polynomials that you can do to represent them. And the key here is that these set of basis functions need to span the entire function space. So somehow you need to know that these basis functions span this space of L2, that they can cover it in some sense. Okay. So then we said, well, let's kind of take a step back from that for just a second, because we're going to find that in this eigenvalue problem, how we're going to find these basis functions. So we said, before we get to that, we need to talk about linear operators. So we had, this function vector analogy, and we said, well, we can extend that to include operators. Operators are like a matrix here. So an operator is something that acts on a function, gives us another function. And we said, we can think about an example differential operator, and went through and made a finite difference matrix. And showed that, or I sort of posited, or tried to give you an intuition, that if I took the limit, as not n goes to 0, but n goes to infinity rather, of that finite difference matrix, that we're going to get back this second derivative operator, okay? But another important caveat is that the boundary conditions change that operator, okay? And so that's going to be important, because we're going to see when we try and solve these eigenvalue problems, that if we change the boundary conditions, we're going to get a different set of basis functions, and that's going to matter. Okay, so now we've sort of got our way to the eigenvalue problem. And eigenvalue problems, okay, eigenvalues problems are important for two reasons. Okay, so we care about them for two reasons. Okay, the first reason that we care about them is that they're going to allow us to find basis functions. Okay, we're going to see that they don't just give us basis functions, but they give us special basis functions. Okay, and so we're going to talk about what that means, but they're going to be like the best basis functions in some sense. Okay, so when we solve the eigenvalue problem, we're going to be able to find what, like Donald Trump would, like best basis functions, right? Okay, and then not just any basis function, they're the best basis function. Okay, and then the other thing that they do is we care about eigenvalue problems because they come up all the time. So practically speaking, okay, we actually care about their answers. So for example, we solved one we saw in the case of the separation of variables. We had to solve an eigenvalue problem. Okay, I kind of pointed that out. We'll go back and look at that a little bit. But there are other physical problems where the whole problem is an eigenvalue problem. So for example, if you remember from your ChEn class, you solved product in a box, okay? And what you're solving is an eigenvalue problem. And all of the different discrete states that you find in particle in the box, those are all different solutions to the eigenvalue problem. So Schrodinger's equations and quantum mechanics the entire field is solving eigenvalue problems, okay? So these methods matter a lot in a lot of these cases. Okay, so recall from, oops, going too fast today, slow down a little bit. Recall from linear algebra, okay, that an eigenvalue problem, I'm going to write eigenvalue problem as EVP because it's really annoying to write eigenvalue problem. The other thing that's kind of annoying about eigenvalue problems is that they put the word eigen in front of everything, right? And so we're going to see there's an eigenfunction, right? And there's, I don't know. Maybe it was a guy Eigen and he was kind of, just obsessed with his name on everything. I don't know. I don't think it is. I think it's just a German word that I can't remember what it means.
I think it means special.
There you go. There you go. Special. It's a special function. Special function. Okay. So the eigenvalue problem looks like this for traditional linear algebra, right? So here we have our operator or a matrix. Okay, let's see. So operator. Okay, here is our vector. Okay, and then the lambda, we almost always use lambda. This is our eigenvalue. I should write eigenvector here. Okay, so sorry for the handwriting at the bottom of the board, but we have this eigenvalue problem where we can solve and get eigenvalues and eigenvectors. Okay, So for infinite dimensional vector space, okay, we have a very similar looking thing. We have LF is equal to lambda. Okay, and again, we have the same thing here. We have our operator. Okay, these two guys are now our eigenfunctions. Okay, and lambda is our eigenvalue. Okay, so for example, we solved one of these when we did separation of variables. Okay, we did d to f dx squared is equal to minus c squared f, where we also had the boundary conditions f a equals 0 and f b equals 0. Okay, so we solved this eigenvalue problem. And you remember what we did, right? We had to solve this differential equation. We got sums of sines and cosines, right? Then we used the boundary conditions, and we found that there was a trivial solution. And then we had to find what the zeros of sine were in order to get those points, and those end up being the eigenvalue. So let me see what I'm supposed to say next. Okay, so I'm not going to go through that eigenvalue problem again, but you can go back and look at that and think about that. And if you remember that the value of c, like we could say that, you know, this is equal to minus lambda, right? So c squared. We did it as c squared in the problem because we ended up having to take the square root. So the eigenvalues, if you remember, the solution here was, I think the c was n pi, right? So the lambda values are going to be what, minus c or minus n squared pi squared. Okay, and then the eigenfunctions that we get out at the end were sine of n pi x. Okay, those are the eigenfunctions. So that's the eigenvalues and that's the eigenfunctions. Yes.
Are you saying that minus c squared is minus lambda, or that c squared is minus lambda?
Well, let's see. This should be right, isn't it? Yes. And this should be minus. Okay, so what I want to motivate for a second is this idea that we're going to get out the best basis function and talk about that a little bit. And to do that, I have to retreat back to regular linear algebra. I have to remind us of something that maybe you covered, maybe you didn't in your linear algebra class. Something that's called the spectral decomposition. So did you guys learn about spectral decomposition in linear algebra? I don't think so. Okay, so it's something that is actually really important. You probably didn't have time to get to because you learn it. Don't you do linear algebra at this, like a lot of times at the same time that you do multivariable calculus? Isn't that what we do here? Teach you in 302. Don't you do both of them in the same semester? So they're like flying through linear algebra and trying to cram it down your throats as fast as possible, and they probably skip spectral decomposition. Okay, so best basis vectors. Okay, that's what we're trying to get at. Okay, and we're going to talk about spectral decomposition. Okay, so I just wrote up here Ax is equal to lambda x. Okay, so for certain properties of the matrix A, which we don't have time to go into, but it would be really fun to take a couple weeks, okay, and do all that math, right? And this is what you would do if you were taking a class on all this. You can show that there are many eigenvalues for that matrix, right? And for certain cases, you can show that there are n distinct eigenvalues. Okay. for A, which is n by n. Okay, so for this n by n matrix A, you can show in certain cases that there are n distinct eigenvalues. And I think the property of this, if I remember, is that it is self-adjoint. Okay, or sometimes also called Hermitian. Okay, and sometimes there's a difference here. I think it has to do with Hermitian are complex matrices and self-adjoint are purely real. But either way, you can show that you get n eigenvalues. So what that ends up giving you is now I can write AXI is equal to lambda I xi, or I equals 1 to n. Okay, so in these certain cases, what this means is I don't have, say, degenerate eigenvalues, where I have one eigenvalue that has multiple eigenvectors, okay? Or I don't have, a defective matrix where I'm missing eigenvalues or whatever, okay? I have n distinct eigenvalues. And sometimes that's also called a perfect matrix, and I can't remember all the distinctions between this because I didn't want to spend all the time. But you can go read about this if this is interesting to you and you want to understand more about the properties that allow us to go from this step to this step. Okay, but just take it for granted for the moment that we can do that. We can write n distinct eigenvalues for this matrix. Okay, yes, please. A is the n by n matrix. Yep. So A is going to look like, n rows and n columns. Okay, and then each of these are 1 by n matrices. Okay, or n by 1 or vectors. Okay, so I can write this. Okay, I can rewrite a new matrix. Okay, I can rewrite a big X matrix, which is equal to x1, x2, all the way to xn, where each of these now are column vectors of the eigenvectors. Okay, and similarly, I can write a eigenvalue matrix, which is a diagonal matrix. And okay, I can write a diagonal matrix where the eigenvalues go all along the diagonal. Okay, I'm allowed to make up a matrix if I want. Okay, and I can show that if I have this, okay, and I write this guy and this guy down, that's equivalent to writing a capital X is equal to X lambda, where now I have a big lambda. Okay. And furthermore, what I can do is now I can multiply by the inverse on both sides of X. So I can write A X inverse is equal to X lambda X inverse. Okay, now X times its inverse is going to be the identity matrix. Okay, so I can get rid of that, and I now can rewrite A as equal to X lambda. Okay, and this is called the spectral decomposition of A. Okay, yes.
I might have missed it because I was writing down the lambda, but how are we able to put the lambda on the right side of X instead of being on the left side? Is it just because we say lambda is a constant? So we can
Here, okay, this is a constant, so I can write it here or here. That doesn't matter. So if you go through and do the matrix multiplication out for yourself, you'll see that to get, lambda X, you need to put it on, you need to do that side of the multiplication. Okay, that's just a property of matrix math because it doesn't commute. So, but we almost always write this problem like this instead of put the lambda on the other side, but that's equivalent, right? So it's just the way it is. Okay, so this one thing you might ask is, can I really take the inverse of this? Okay, and it turns out that the same properties that guarantee that you can do this step, meaning that you have n distinct eigenvectors, so they're all linearly independent eigenvectors, means that you can then take the inverse of this matrix and write this way. Okay, so we know that that matrix has an inverse if we're allowed to do that step here. So that's one of the important pieces of the math. Okay, so what else to say about this? Okay, so 2 comments about this real quick, and then I'm going to show. Okay, the first comment is that this is sometimes also called by another name, which is normal mode decomposition. Okay, so I kind of want to talk a little bit about terminology. So first, I didn't say this spectral decomposition in math language. When we say something with spectra, spectrum, spectral, we're almost always talking about eigenvalue problems. Okay, so the spectrum that we're getting are the eigenvalues. Okay, so this is a spectral decomposition. It's a decomposition into eigenvalues. Okay, this is also sometimes called a normal mode decomposition. What we're going to find out, or maybe I'm just going to tell you, is that these eigenvectors that we found here are going to be orthogonal eigenvectors. So this same math that says I can do this also means that these eigenvectors are all orthogonal to each other. Or in other words, they're normal, okay? They're orthogonal. And each of these is a different mode, okay? So these different eigenvectors are different modes sort of the solution. What we've effectively done, if you think about this, is we've decoupled the problem. And that's what I'm going to show next, okay? So we're going to, by doing this decomposition, when we have some problem AX equals B, we're going to decouple all of the solutions. We're going to be able to solve it by diagonalism, okay? And so this is a really powerful method for solving things. So for example, you can apply this spectral decomposition to a set of coupled differential equations, okay? And if you do a normal mode decomposition or spectral decomposition, you can find a new set of differential equations that are all completely uncoupled, and you can solve them individually, okay? And then this insight in these normal modes is applied all over the place in science and engineering, okay? And they're even used to think conceptually about problems. So maybe one that you've heard of is phonons, okay? So I don't know, have you ever heard of phonons in heat transfer? Did you guys ever talk about that? Okay, so maybe that won't help any, okay? But when you're talking heat transfer, you talk about conduction in a solid, okay? And there's a lattice of atoms in a solid, okay? And they're vibrating. And you can think about, instead of thinking about that whole lattice, you can think about individual particles that are sort of moving in the lattice instead. You think, well, what does that mean to have these other kind of particles, okay? And they call them phonons. And what those are is they're the normal modes of the vibrations of those lattices, okay? So if you ever come across phonon theory, there's that. Let's see, is there any other? Orbitals. You've certainly heard of orbitals okay? Orbitals are the normal modes, okay, of electrons around an atom, okay? So all the orbitals that you learned are the normal modes of the hydrogen atom. That's the ones that you learn in freshman chemistry, okay? So hopefully we'll get to actually see where those come from at the very end, okay? So,
There's no question.
yes.
So the key to go from PDEs to ODEs to go to differential.
Is this the key? So this is not the key to going from PDEs to ODEs. We got the PDE to ODE because we assumed that temperature and, or excuse me, time and space were a product solution. That's what allows us to go to the ODEs. But we needed to then solve one of the ODEs, which gave us an eigenvalue problem. What we're trying to find out here is what are the different basis functions that I might use if I have different geometry, okay? And so what I'm going to need to do is to solve some kind of eigenvalue problem and find what the eigenvectors are. So if you think about this, this is like all of the basis functions, okay, in some sense. And what I'm trying to show, and I'm going to show a quick example here, is how these are like the best basis functions in some sense. Okay, and it's going to be because they do this decoupling. Okay, so the other thing I was going to say, I think I just said in words already sometime, is that the eigenvectors x1, x2, xn, okay, form a complete, okay, and orthogonal basis set. Okay, so for the vector space of interest. Okay, so that's the other thing that's important. And this follows from nothing that I've proved, but this follows from what I said earlier about having this kind of matrix. Okay, so this matters because I have a self-adjoint matrix. So let me show you about this decoupling with a linear algebra problem. I'm going to motivate this. Show why this spectral decomposition is useful. Okay, so suppose I have a linear problem. That's supposed to be an M problem. A, Y equals B. Okay, I'm going to use a Y because I've been using X for eigenvectors, so I want to keep it separate. Okay, so suppose that instead of expressing Y, like normally we would write Y in components, right? We would write Y something like the sum over some coefficients times some unit vectors like X, Y, and Z. Okay, so normally that's what we would do, right? So suppose I don't do that. Suppose instead I write yi as some sum over some new coefficients, which I'm going to call yi prime, okay? And I write them in terms of the eigenvectors, xi. Okay? So now instead of doing, the x direction and the y direction, I pick the eigenvectors that I get from this A matrix, okay, and use them to express my problem. So now these yi's are, the different, how much in this direction of that eigenvector and how much in this direction of that eigenvector do I have. So maybe to kind of think about it in just a 2D space. Previously, I had E1 and E2 here, okay? Suppose now my eigenvectors are like this. Suppose I have x1 and x2, right? It's just some different set of vectors that are the eigenvectors of A, and I'm now picking to represent my, new vector, what is I call that y, suppose that's y. Now it's going to have, those components instead of the other components from the E1. But this is the same vector, right? Just expressed differently. Okay, and I can do the same thing for B. So I'm going to make B equal to the sum over the I prime xi. Okay, same thing, all right? Now this, I'm saying here, this is a vector y in terms of these x, but I have this sum. What I'd like to do is rewrite that sum as a matrix vector product in terms of these x matrices, okay? So I can do that pretty easily, actually. I'm just going to write that y is equal to x y prime. Okay, and B is equal to x B prime. Okay, so now I've written this y in terms of that product there, and it's y prime and B prime. These are the coefficients, right? So now it's a vector of all those coefficients that I'm adding. And what I'm going to do is I'm going to substitute these back into this equation and see what happens. Okay, so let's write that down. So I have A x y prime is equal to x b prime. Okay. So now I'm allowed, since X has, or actually I'm going to do the following. I'm going to take this A, I'm going to substitute in my spectral decomposition. Okay, so let me do that. I'm going to have X lambda X inverse multiplied by X y prime is equal to X b prime. Okay, so now I look at that and I have X inverse X, that's the identity matrix. So that stuff's going to go away. Okay, and I can multiply, left multiply by X inverse. Okay, when I multiply by, left multiply by the X inverse X is also the identity matrix. X inverse X is also the identity matrix there. And what I get is lambda y prime is equal to b prime. Look at what I just did. I just diagonalized the problem. Right? Lambda is this matrix with only lambda on the diagonal, each of the eigenvalues on the diagonal. Okay? And so what this means is this is the same thing as writing, you know, lambda 1 y1 is equal to b1, lambda 2 y2 is equal to b2, etc. for all of them. Lambda n yn is equal to b. Okay, so by expressing these y's in terms of the eigenvectors, okay, instead of in terms of whatever basis I wanted, I ended up being able to write it now as completely decoupled equations, right? Now I can solve for whichever one I want without having to mess with any other one, okay? So in some sense, this basis set, this complete orthogonal basis set that I get from the eigenvectors is actually the natural basis set that I'd want to express the problem. Okay, it's the one where I don't have to worry about inverting a matrix. It's already done for me. Does that make sense? So that's the takeaway from this part. Okay, is that if I can express my vectors as a sum of eigenvectors, okay, the problem is greatly simplified. Okay. And also, by the way, so it's uncoupled the problem. Okay. It also often gives us physical insight. I think where we'd be in chemistry if we didn't think about orbitals, right? So by thinking about those normal modes, that gives us physical insight into the problem. Okay. Questions about the eigenvalue problem in general? About the spectral decomposition. So like one thing you could do, if I had written a homework problem, one of the things I might have done, okay, is to say, go play with Python and make up a matrix like A y equals B, okay, and then use Python and their eigenvalue and eigenvector functions and figure out what X and lambda are, okay, and then play around with it. Do this, you know, see if that's true, okay, play around with different matrices, you know, see if you can look up what self-adjoint means, find a self-adjoint matrix, okay, see if that's true, see how that decouples these problems, you know. Anyway, it's an interesting thing to kind of play around with and see what happens when you can do a spectral decomposition. Python makes it really easy because NumPy has the eigenvalue and eigenvector solvers. They're super easy to use. So anyway, that would be a fun thing to do. Got a few minutes, you're not stressing out about kinetics or something.
What do you mean by uncoupled or decoupled?
So if I have an equation like Ax equals B, right? I usually have A11 x1 plus A12 x2 is equal to B1. Right? So I have to simultaneously solve for x1 and x2, right, to solve this. That makes it hard to solve.
Okay.
When it's uncoupled, I rewrote this in a new way, where I had some new coefficient, I don't know, A1 prime, Y1 is equal to B1. Right? So now I have it so that it's trivial to solve for Y1 in this case. Right? So that's really simplified the problem. And you can get physical insight sometimes because, for example, sometimes only one eigenvector dominates the entire problem, right? So maybe, now you can just say the solution to this entire mess of things only really matters if I have one. That's actually a really common assumption. If you have one eigenvalue that's really large, the others are really small, then you end up with a thing where, if I have, suppose I had this case here, right, where I had x1 and x2, suppose those are my eigenvectors, right? If I have one really large eigenvector or eigenvalue, that means that my, vector is almost parallel to that eigenvector, right? And so that eigenvalue is really large, the others are really small. So that means pretty much solving the problem for that eigenvector tells me all I need to know, okay? And then maybe just a little bit of corrections due to the other eigenvectors. So there's a lot of things you can do once you can do an eigenvalue decomposition. Question?
Please, can you vocally repeat your takeaway?
The takeaway. Yeah. So the takeaway, I'll say it one more time. Make sure I get it right. Okay. So if I can express my vectors as a sum of this eigenvector basis set, my problem gets a lot more simple. Okay. So the eigenvector basis set is like, I wrote in my notes, it's like a magic basis set, right? It somehow gets rid of all the coupling and it simplifies the problem. Okay. So whoever that was, here you go. Okay. Okay, so now we're ready to talk about the Sturm Liouville eigenvalue. Okay, so that question here is, so what the heck does this have to do with PDEs? Okay, so think about the following. What if I could write the solutions to those PDEs in the basis set that corresponds to that linear operator? Okay, so if I had, this linear operator, okay, and I said I knew that FA equals 0, FB equals 0, okay? If I could find that basis set, right, and then I wanted to, like, if I knew what the basis set was, okay, then if I could write my answer as, f of x is equal to sum over ci phi x, okay? If I knew that basis set, I could plug it in right there, and my problem would get a lot easier, right? So I want to be able to solve sort of the eigenvalue problem for, PDEs, okay, for two reasons. Right? The first is I want to find any phi of x that is complete and orthogonal. Okay, that was Zach's question, right? How do I find any, any of them? Okay, but the second one is if they are eigenvectors, or eigenfunctions rather, they're eigenfunctions of L, okay, then they will simplify the problem. Right? So if I can solve that eigenvalue problem for functions, I can do both of those things. I can find these, but not just find them. I find like the best ones, right? So let's think about that for a second. We solved this problem here where we said, let's look at an example of this. I had this problem before, d phi dt is equal to p squared phi dy squared. We solved that guy, right? And we said eventually we want to write phi as some sum from n equals 1 to infinity of some coefficient, right? So we're going to write the sum over n instead of I. We call that coefficient. And we wanted to do it with some basis functions, right? Well, what basis function? We ended up solving for it. It was sine of n pi y. Well, what if I started with this? If I knew what the basis functions were, as opposed to doing this whole separation of variables nonsense, suppose I start with that and I express it there. Now let me take this and plug that in here and see what happens. Well, let me take the time derivative. Well, the time derivative, this Cn, that could depend on time. Okay, I haven't said anything about that, but that clearly doesn't depend on time. So if I take the time derivative of the sum from n equals 1 to infinity of Cn sine of n pi y, I'm going to say that that's equal to the second derivative with respect to y, the sum of n equals 1 to infinity of Cn sine of n pi y. Okay, so if I do that guy, I say, okay, time derivative, the Cn is going to come out, so I should just have the sum from n equals 1 to infinity of d Cn dt multiplied by sine of n pi y. And over here, this Cn, that's got to be a coefficient, right? Because it doesn't depend on y, so it can't depend on y there. So I'm going to have to just take the derivative of the sine, right? So I pull this in here. The second derivative of sine is minus sine, but with the coefficients out front, right? So this is going to give me the sum from n equals 1 to infinity of Cn times minus n squared pi squared sine of n pi y. Okay? When I look at that, I have a sum of 1 to infinity on both sides of this thing multiplied by n pi y. So I can actually pull that out. I'll do it up here. I can write a differential equation for the coefficients, which is Cn n squared pi squared. I can get that dCn dt is equal to minus Cn n squared pi squared, right? Well, now that one I can solve right away. I know how to do that. And that differential equation, right? That's going to give me Cn is equal to some coefficient, An, exponential of minus n squared pi squared t. Okay? And now all I need to do is apply the initial condition, which is what I did, at the very end last time. So to find the Cn, use, inner product to find the initial condition. Okay, and so there we just solved the separation of variables problem in 5 steps. Okay, on one half of the board, and it took us an entire 2 classes to do the separation of variable problem last time, right? So if I know this, eigenfunction, and the decoupling step happens right here. Okay, this is decoupled now, right there, because look, I have signs here and signs here, and so this equation, there's no matrix anymore. Okay, there's no matrix over here where I have different double sums over anything. This is exactly equal to that side, so I can pull out the DC and DPs, and I've completely decoupled them. Okay. If I had picked something that was wrong over here, like cosines, okay, when I went to do this, I would have an issue. Okay. Actually, cosines ends up working, but for different boundary conditions, so that would work out. But it wouldn't satisfy the right boundary conditions, so cosines would work. But if I pick something like x cubed or whatever, okay, that wouldn't necessarily work out on both sides, and I couldn't equate those. So, does that make sense? Okay, so we're out of time on this. So what we're going to talk about, we're going to finally get to Andrew's question, okay, at the beginning of next time. we're gonna say, so how do I come up with these different functions then? Okay, and it turns out that there's an eigenvalue problem that expresses all of the problems we care about. And we can show how that will lead to some different examples and what the different eigenfunctions are. Okay, and so we'll finish that next time and show what those are. Sorry, I took an extra 2 minutes. But I figured we wanted to see that little. Hey, thanks, guys. Have a good evening. See you.
I don't know, like, it's not,
Oh, he's gone.
yeah.
Email me. He knows how to email.